Hello and welcome to Rad in Action Unit Testing in Delphi. I'm Nick Hodges, a senior software engineer with Viva Systems, and today I'm going to be talking to you about just that, unit testing in Delphi. Here's the agenda for today. First, we're going to talk about what is unit testing. That'll involve as well some definitions. Talk about why you want to do unit testing, what the advantages are. Talk a little bit about how you do it. We'll look at unit testing tools and frameworks with Delphi. And then we'll have some coding examples showing you exactly how we do these techniques. So here's my goal today. I want to make you feel like this guy running down the street without your clothes on if you're not writing unit tests. Unit tests provide you an enormous amount of protection, comfort, and benefit. And if you're not doing them, I want you to feel like you're running down the street naked. So the first question you may have is, what is unit testing? Well, I'm going to tell you. Here's sort of the academic version of unit testing. That's the testing of code units in isolation to ensure that your code works. Please note that I'm not saying that your application works. I'm saying that your code works. Unit testing is the testing of code, not systems, not applications, not the integration of things together. Unit testing is also part of a larger testing effort. I want to make that clear, that unit testing is just one part of the different types of testing that you do, including integration testing, regression testing, acceptance testing, and all those other different kinds of testings. Unit testing is also something that proves that your code works properly. I mentioned earlier that unit testing tests your code and not your application. And so if you want to know that your code is working properly, you do unit testing. Unit testing can also act like bug repellent. Whenever you write a big suite of unit tests, those tests can quickly and easily reveal when a change results in a bug. A complete and thorough suite of unit tests will also help to ensure that any bug that creeps into your code will be revealed immediately. When you make a change and a bug is introduced, the unit tests can reveal them right away. Of course, finding bugs early makes them easier to fix. Unit testing will also find existing bugs in your current code. If you have a suite of code that you haven't written unit tests for, you can write unit tests for that code, and those unit tests will help reveal bugs in that code library. Proper and complete unit testing will also explore the edges of your code to make sure that it works in all circumstances. For instance, you might want to check to make sure that your integer math works at the very edges and boundaries of the integer numbers themselves. You might want to test the edges of a rectangle class, seeing whether the class performs properly when a point is just inside the edge of the rectangle or actually on the edge of the rectangle itself. The edges of your code are the places where errors are most likely to occur or can occur, and you want to make sure that your unit test coverage deals with those situations. This is an interesting side benefit of unit testing. Unit testing can document the proper use of a class. Oftentimes I'll be looking at a open source project. The first thing I'll do is go to the unit tests, because the unit tests will often show you exactly how the code should be used and called. So when you write unit tests, it's like writing documentation for your class. This is probably the most controversial thing I'll say about unit testing, because this is the most contentious amongst the developer community and management, and that is that unit testing saves time. Many developers believe that writing unit tests takes more time than it saves, but I don't believe this, and in fact I'm going to argue the opposite here. Writing unit tests helps ensure that your code is working as designed right from the start. Unit tests define what your code is supposed to do and immediately ensure that your code does it. Every unit test you write becomes a regression test, ensuring that down the line all of your code will continue to work and that it won't break when changes are made. All of these benefits save time in the long run, enabling you to move forward with changes and additions to your code with confidence, because you know that your code is working correctly at all times. You already test your code as you're writing it. You might write a simple console app. You might compile it and see it running. You're always testing your code. You might as well take that time and write good unit tests, because they'll have downstream benefits for years to come. Having a full, complete, and thorough set of tests that cover the complete functionality of your code might be difficult to achieve, but having it will give you peace of mind. You can run those tests anytime you want and know that your code is working correctly. You can make changes, do refactorings, and know that your code is still working properly. Knowing that, despite what you might do to your code, gives you peace of mind. All code changes and ages, but legacy code only occurs when code does not have unit tests. And in order to keep your code from becoming legacy code, write unit tests for it, and you can have the peace of mind that that code will continue to work no matter what changes are made to it. This benefit of unit testing is probably the hardest one for people to see and understand. It's one of those things that you learn as you go along, but unit testing causes you to design your code properly. It's a very happy coincidence that testable code is also well-designed code. If you write your code to be testable, you'll write it in an uncoupled fashion. You'll write it in a way that requires simple, smaller modules. You'll write it in a way that is well organized. Testable code, i.e. the code that can be unit tested, is well-designed code. And you'll find this as you go along. The more tests you write for your code, the better designed your code will be. Okay, so we've been talking about unit testing and sort of what its benefits are and why you should do it. But let's look a little more deeply at some of the definitions that are involved. The most obvious question to ask at this point is, what is a unit? Well, a unit is the lowest level of code that can be tested in isolation. And normally, this is a single class method. We'll use this definition, that is that of a single class method, throughout our demonstrations and the conversations that we'll have today. In addition, we'll be discussing what it means to test a class method in isolation. A little later, we'll be talking about isolation frameworks, or more commonly mocking frameworks. And so we're going to need to know what a fake is. Well, a fake is any class that provides functionality sufficient to pretend that it is a dependency needed by the class under test. There are two kinds of fakes here we're going to talk about: stubs and mocks. A fake is what you use in order to test your class in isolation. You don't want to do unit testing based upon something like a database. So you use a fake to pretend that the database is there, and those fakes can enable you to write your unit tests without depending on the actual database itself. A stub is a specific kind of fake that has no effect on the passing or failing of the test at all, and all it does is exist purely so that you can actually run your code. If your code requires a logging tool and you don't really care about testing the logging while you're testing the main functionality of your specific method, you can pass in a stub for the logging tool, and the logging tool will do nothing. That stub will do nothing, but it enables you to run your code because your code requires that logger. While you often hear the term mock used in the general sense, a mock is actually a specific type of fake. Mocks are a little more complex than stubs in that they actually determine the outcome of a given test. You pass a mock into the class that you're testing, and when a test is called, the mock checks the behavior of the class under test and determines if the class behaved correctly. If the class behaves correctly, the mock says, yes, the test passed. If the class behaves incorrectly, then the mock will fail the test. So a mock is a fake that can actually fail a test. And we'll see a little bit more about how these mocks and stubs work in the code demo. Next up is the question, what is test-driven development, or TDD? You see that a lot. It's a common term that's bandied about, and I don't mean this to be a treatise on test-driven development. You can decide whether you want to write your tests first or during or after you write your code. That's all fine and good. I'll just go real quickly through what test-driven development is. Basically, it's the notion that you write your tests first. You write a test, you run it and it fails, you write code, and you watch it pass until it passes, and then you write some more code and you watch it pass, and so this little loop takes place down here. And then once you get done, feeling confident that that particular test has been coded to its maximum capability, you start back up at the beginning and you write another test, watch it fail, write some code, repeat this loop here until you're ready to write another test. And the idea then is that the test drives your code. I'll actually show a quick demo of this in the code portion, but the notion is that your code is a result of the tests, and that's how the notion of decoupled testable code comes about. If you write tests first, you can't help but write testable code, and as I said earlier, if you write testable code, you're writing well-designed code. So there's a quick look at some definitions and terms that we'll use throughout the presentation today. The next question that probably comes to mind is, am I actually doing unit testing? And this is another topic that is commonly discussed. I mentioned this earlier, and I'll talk a little bit about it coming up. But you're doing unit testing if you're testing your classes in isolation. If your test requires any external entity other than an isolation framework, then you are doing integration testing. Now, I don't mean to denigrate integration testing. You should do integration testing. But before you do integration testing, you want to do unit testing. You want to test each class in isolation apart from any dependency that it has in order to make sure your code works correctly. And from there, you can go on and do integration testing, regression testing, acceptance testing, whatever kind of testing you want to do. But the trick to doing unit testing is to test your classes in complete isolation. In other words, you should be able to take your unit test executable, put it onto your grandmother's computer that has no notion of Delphi or runtimes or anything at all on it, and run that executable and have all of your tests pass. That is running your tests in isolation. Okay, let's dig a little deeper into this notion of testing in isolation. So here's a quick graphic that just shows your test driver or your test framework, which provides some stimulus to the class under test, i.e. it pokes it, it runs it, it does something to it. And then that class under test is checked. You use your checks or asserts to see if the results are as you wish them to be. And that's just the basic notion of a test. However, part of the problem you run into with this test is the idea that your class can oftentimes have secondary effects. In other words, the class under test might need another class that then in turn requires an external database, a second class that then in turn does some type of CPU intensive process or talks to the file system, or another class can require another class that then in turn requires some external server on your system. Anything can happen on the back end of testing a given class. The trick to testing your class in isolation, making your test testable in fact, is to write your classes with the notion of this seam. And as you can see here, there's a notion that your class is separated from all of its dependencies very cleanly and very easily. Once you do that, you can then either note that the dependent classes are friendly classes that don't cause any harm. There you can put in a stub class or a mock class in place of classes that might cause external dependencies on other servers, such as a database or a file system or something along those lines. In this way, you can isolate your class using an isolation framework, i.e. the stubs and mocks, that pretend to be the dependencies that your class have. And as long as you're writing your code in such a way that you can stub and mock out all your dependencies, then you are testing in isolation, you're writing testable code, and you're writing well-designed code. Okay, so we've talked about what unit testing is, what unit testing is not, why you want to do it, all those fun things. So now it's time to actually get down to the nitty-gritty and talk a little bit about how to write good tests. So here are some tips for writing good unit tests. First, only write one check or assertion per test. This is kind of controversial again as well, because oftentimes people do a lot of setup work and they want to run more than one check or assert in any given test. But I encourage you to resist that temptation. I encourage you to use the setup and teardown features to do your setup and teardowns, and allow only one check or assert per test inside of each individual unit test. Secondly, you should use the AAA principle, the AAA principle, which is arrange, act, and assert. So the first thing you need to do in any given test is arrange things so that the test can be run. Set your expected results, your expectation for the result. Act is actually call the method itself in order to run the test. And then the third thing you do is assert. That is, check to make sure that the result is what is expected. Here's another good tip. Don't put logic in your tests. If you're using an if statement, for instance, or some type of case statement, then you're running more than one test inside any individual test. If you feel the need to have logic or if statements inside of your tests, then you need to rethink how you're doing things. Your unit tests should be easy to run. You should be able to run them at the command line very quickly. You should be able to run them using the GUI test runner and see your nice green bar running across this from left to right. If tests are easy to run, you'll run them frequently. If you run them frequently, you will find bugs almost immediately. You'll see problems very quickly and you'll be able to fix them right away, knowing what recent changes you made. Write down the middle tests first. That is, write the tests that are sort of sweet spot in your tests. If you're doing addition and subtraction in a math unit or something, you might want to make sure that 2 plus 2 equals 4. That's sort of a down the middle of the plate test. Do those first, and then follow those up with tests at the edges, as we discussed before. Start testing things around 0. Start testing things around max int. Start testing things at the edges of what your class does, the extreme cases. Follow that as testing across boundaries. If you're doing addition and subtraction, as we'll do in our demo, we're going to test to see what happens if you add a positive number and a negative number together and make sure that that works correctly in our algorithm. If you can, test the entire spectrum of your class. Test everything that it can do. If your class has a enumerated type, write tests that check to see what happens when every value of that enumerated type is used. Sort of along those lines, try and cover every code path. If your code has an if statement in it, make sure you test both sides of the if statement. You can use a code coverage tool, run that against your unit testing executable, and it'll tell you what code paths in your class are not currently being used. Delphi has a good code coverage tool. Use it. Write tests that reveal a bug and then fix it. This is a very excellent technique. If you find a bug in your code outside of your unit tests, write a unit test that fails because of that bug. You can then quickly and easily debug that test, fix the bug, and then you'll know when the bug is fixed because your test passes, and now you have a regression test for later to make sure that bug never comes back. All tests should be independent of each other. You should never have to run tests in specific order. If you do have to run your tests in a specific order, you're not doing your setup and teardown properly, and we'll see how that works in the coding portion of the presentation today. All tests should be independent and able to run individually without any dependencies on other tests or anything at all. If you're going to raise exceptions in your code, test that. Create a situation in your arrangement, in your arrange portion of AAA, whereby the exception will be raised by your code, and ensure that it is indeed raised under the circumstances for which it is supposed to be raised. As I mentioned earlier, tests should never depend on each other. They should always be independent, and they should never rely on anything other than themselves. Again, that just gets back to the test in isolation. Use good names for your tests. Don't be shy about naming them. Don't be shy about having a nice long name such as divide by 0 raises an exception. Have that be the name of your test. Good names for your tests help you find and understand what happens when a test fails. If you just name your test test division, that could be anything. But if you name your test customer must have proper customer ID number, then you know exactly what's going on when the test fails, and you get a report from the test harness. It tells you exactly what test failed. It tells you exactly what the problem is, and you're well ahead of the game for fixing things. Run your tests constantly. Since they're easy to run, you should run them frequently. You should run them after every time you change code, really. They should be easy to run, easy to check the results of, and you should run them all the time in order to ensure that they're all always passing. Never allow your code base to get far away from passing tests. Run them as part of your automated build. Surely you guys are doing automated builds, and you should be. Run your tests and if your tests don't all pass, then the build is broken. That should be part of your automation continuous integration process from the very beginning. Bottom line on all of this, if it's hard to write tests, then you're doing it wrong. If writing tests is difficult, then you've written your code in such a way as to not be testable, and if your code is not testable, it's not designed well. I realize that there's a lot of existing legacy code out there that's hard to test, but if you're writing new code and you are not writing unit tests in an easy, straightforward manner, then you need to rethink how you're writing your code so that you can write testable and thus well-designed code. Okay, so we've talked a lot about theory so far. Let's talk a little bit about the specific tools and frameworks that you can use to unit test in Delphi. First up is DUnit. DUnit's been around for many years. first written by Juan Carlos Añez back in the 90s with the help from Kent Beck himself. And it is a venerable tool integrated right into the IDE, and it enables you to write unit tests, execute them either at the command line or using a graphical user interface with the green bar that everybody loves to see. We'll demo DUnit in the coding portion of the presentation coming up soon. DUnit is an open source project available on SourceForge, but it has languished as of late and has not been updated in some time. There are some projects that expand upon it, but the actual project itself has not been updated in quite a while. However, it is a perfectly serviceable and usable unit testing framework, and if that's the one you choose to use, I think you made a wise choice. More recently, there has been a project called DUnitX from Vincent Perret of Final Builder fame. This uses the new runtime type information inside of Delphi since Delphi 2010, and it relies on attributes to tag specific classes and methods as test fixtures and tests themselves. This is the unit testing framework that I'm using going forward, and it's the one I recommend that you do use. It's still a work in progress. There is not a GUI test runner just yet, but that's in progress and in work, and this is the more modern way of doing unit testing with attributes. We talked about isolation frameworks a little bit with mocks and stubs, but I'll give a formal definition here. An isolation framework is a collection of code that enables the easy creation of fakes. An isolation framework, more commonly called mocking framework, but mocking, of course, as we've seen, is only part of the story, is one that allows you to test your code in isolation. It allows you to create fake dependencies to isolate your classes so that they can be tested independently. Currently, the most popular Delphi isolation framework is called Delphi Mocks. It's available on GitHub, again from Vince Perret and the folks at the Final Builder, and we'll see it in use in the coding demonstration coming up soon. There is, in addition, an isolation framework built into the D# repository on Bitbucket, built by Stefan Glenke. If you're interested in some of the things that go on there, you can take a look at that. We will be demonstrating, however, the Delphi Mocks framework in the coding portion. So here's my final advice before we head off to look at code. And that is, first, only test the code that you want to work properly. If you want your code to work properly, test it. And then don't test the code that you don't want to work correctly and have cause all kinds of problems down the road. If you got some code that you don't care about, that you don't care if you have to maintain it, you don't care about causing problems and all that kind of stuff down the road, having it quickly become legacy code, unfixable, unmaintainable, then don't test it. Don't bother writing unit tests for it. Okay, from here we're going to move into the code demo portion of the presentation, illustrating some of the points that we've discussed so far. So the first thing we're going to do is run through a very basic test-driven development scenario to give you the feel of how test-driven development works and how, in this project, DUnit works. So here I have an empty basic console application to which I'm going to add a new unit. I'll save that unit. I'm then going to create a very simple class called tCalculator. And to it I'm going to add a single function called add. It's going to take two integers and it will return an integer. And I'll use Control-Shift-C to create a stub for it there. At this point, we don't want to do anything. We want to write a test first before we begin. So I'll save this. I'll then go to the project group and I'll say File, New, Other. I'll go down to the unit tests and I'll create a new test project based upon Unit 7, or Project 7. And then I'll create inside of that a test case, and you'll notice that the IDE is smart enough to build for me unit based on tCalculator with add as its method, and it creates this automatically for me. And you'll notice that it creates completely the new test case. I'm going to save the whole project. It creates a new test tCalculator class, descends from tTestCase, which is the base class for all test cases in DUnit. And it has a setup project, and it has a setup method and a teardown method that are used each time a test is run. It calls setup and it calls teardown. That setup and teardown, of course, are going to create and free, we don't need to nil it, the calculator. Then it creates a test add method, which takes the two parameters that we need to pass, or gives you two parameters that we need to pass, and this calls the actual method itself. So actually what we want to do is a little housekeeping here. First, of course, using our AAA, we want to arrange, act, and then assert. That's what we'll do here in a minute. Well, let's do it now while we're here. Arrange is x gets 2, y gets 2. So we arrange things. We set an expected value of 4, and we'll use a refactoring to declare that for us. And then we want to act. That is, we want the return value to be whatever the method under test returns. And then we want to assert. We want to check true that expected value. I'm sorry. Let's use check equals, because we don't want to return false when we actually want to see what the actual values are. So we'll pass in expected value and return value, like so. Now we have a test. However, this isn't a very well named test. This is something that tests adding 2 and 2. So we will use the rename refactoring to call test adding 2 and 2. That should tell us exactly what that test is doing. And then when it comes time to debug the test or find the test runner will tell us exactly what the test's name is, and we know that what that test is doing. So now we can run this. We'll get a GUI debugger, and you can see the test fails, of course, because we have no code. Okay, so now we have a failing test, and let's write the absolute minimum amount of code necessary to make that test pass. That's the first step in test-driven development, right? The absolute minimum amount of code necessary to make your test pass. And that would be that. So here we go. I wrote that code. We run our test. Yay, test passes. That's great. Okay, so we've got a test written, runs, and it passes. So let's iterate again. Let's write another test and see what happens. Looks like I forgot to press the button on that refactoring. So let's do it again. Just declick that and just run the refactoring. Okay, so now let's add another test to refine our algorithm a little bit. See what we do. Test adding negative and positive numbers. So let's do a little, test across boundaries. And I'm going to commit a cardinal sin. I'm going to copy this code just for the sake of expediency here. And I'm going to change this to, say, a 5 and a -1. So we're going to add a positive number and a negative number, and we should get the result of 4. Only I'm going to make this -2 just for fun. And we should expect a different result of 3. So now we should be able to run this, and we should see our tests. One passes, and uh-oh, one fails. Expected 3, but actually was 4. Well, that makes sense, because if we go back to our addition algorithm, we find that it's a little simplistic. Bear with me here. This is just a demo. It's a little simplistic. So let's fix that so that our test passes. I'm going to use this algorithm that my math buddy taught me. I'm going to use the absolute value of x plus y as my algorithm. That way I'll be absolutely sure that it's right. So, yay, now we're done. Now we'll run it again. And now we see, hey, our tests pass. So what do? We write another test. Let's write another test that tests the boundaries. What happens if I write a test called test adding 2 negative numbers? Oops, I guess I should implement that. And once again, I'm going to copy this code just to save time. I'm going to add two negative numbers, -2 and -4. That should equal -6. So let's see how we can do there. I will run it, run the tests, and that last one fails. I'm expecting -6, but it was 6. Well, now I can go back and refine my algorithm a little bit again. How about x plus y? Actually, so I just had a math buddy of mine. I'm going to go and get a PhD in mathematics to tell me that the algorithm should be x plus y minus 6 plus 3 plus 3, like so. Okay? And now I've done that. Now I'll run my tests, and all my tests pass. That's really awesome. So now I've got this ready to go. I've written some good tests that kind of test the boundaries and edges and that kind of thing. You can imagine some other tests that you might want to write that would do that. But I'm good. My tests are passed. I've got the basic down the middle test. I've got some edge tests. They all pass. Now here's the fun part, right? Let's put this into production, and you notice some inefficiencies. You notice that your math is not running, the addition thing is not running quite as fast as you think it should. And you go and you examine it, and you realize that this algorithm here is not really all that really good. I mean, there's that -6 plus 3 plus 3 part there, and you're like, why am I doing that? So the PhD told me to do it, but gosh, I don't know. Why am I doing that? And you want to refactor your code. You want to change your algorithm. Well, you can. I can now go in and just change my algorithm quite radically, actually. That's a radical. Think of that as a radical change to your algorithm, to your code that you want, the results that you want. Well, you've got a suite of tests. So you can save that. You can run your tests, and you've refactored your code, and you see that your tests all pass. And now you have confidence that your changes, your refactorings, have worked correctly because your tests all still pass. That's test-driven development in a nutshell. Okay, so we used DUnit for this project, or testing this project. What would the tests look like, and how would this project look if we were to use DUnitX? Well, let's take a quick look at that. We can create a test project for project 7 here by going to the IDE, and DUnitX ships with a small, simple expert that creates a DUnitX project for you. So let's do that. Let's double click on that. We want to add it to the existing project group. We want to create a test unit. We want to create setup and teardown methods just for because we need them. And we're going to call it TMyTestObject. I want to use, whoops, I'm sorry. I want to go ahead and add in unit 6 to this project because unit 6 is our calculator. And inside of unit 7, which I'm going to save, I'm going to use unit 6 inside unit 7 so that we can see it. So what we have here now is a simple class that descends directly from TObject, but that has attributes attached to it. The first one here is test fixture. This attribute defines and declares the TMyTestObject class as a test fixture, a harness, a class that contains tests. And you'll notice that there's a procedure called setup and a procedure called teardown. They are tagged with the setup and teardown attributes as well, meaning that is the setup and teardown procedures. The setup will be called every time a test is run, before every time a test is run, and the teardown will be called every time after a test is run. So we need to declare a private variable called fcalc of type tCalculator. And in the setup, we will create an instance, fcalc gets tCalculator.create, and in the teardown, we'll free it. Now, in order to add a test to this very simple class, all we need to do is declare a attribute called test, and we can go procedure 2 plus 2, or we'll call it adding 2 plus 2, excuse me. Test adding 2 plus 2, just like we did before. And we'll create the test. Now here, instead of using the check methods, we use a class called assert. And assert are equal. And we'll expect that the answer is 4. And we'll test fcalc 2 comma 2 as a result. This is just throwing in this real simple test fcalc.add like so, and that'll run the test. And you'll see the DUnitX doesn't have a GUI runner yet. It does have a nice pretty console output though, and you can see that the test passed. It's nice and green, and that one test passed. So that's how you use DUnitX. Instead of descending from a specific test class, test case class, as you do with DUnit, we declare attributes that define the tests and the setup and the teardown. And there's actually more attributes. There's a fixture level setup and teardown that gets called once each time for each fixture, and as well as some others that are being added. DUnitX, as I said before, is still a project in work, but it's very cool and it's very easy to set up classes using DUnitX as test fixtures. You simply declare the attribute, tag any methods you want in your class with the attributes that you want them to have, and they become tests quite quickly. It's very, very easy, very, very simple to use, and it's very powerful. So I'm going to press forward with DUnitX. So let's take a little closer look at it. For instance, let's take a look at the source code for the project. You'll notice that it includes the single class that you do need for DUnitX in the code that you write, that is DUnitX.testFramework. It also includes the test runner, which contains the class that creates the runner. It contains a NUnit output as well as a console and a logger console. In order to have a project that uses DUnitX, you need to create a runner, have it use RTTI, that signals to it to use the new RTTI. We're going to use a console logger as the logger, and we're going to use a DUnitX file logger as well by default. We're going to add the two loggers to the runner, and then the runner just executes. And in this case, we're going to write out to the console as long as we're not using continuous integration. That's what the project looks like. Here's a quick look too at the assert class. You'll notice that it is a class with nothing but class procedures attached to it, and a large number of overloaded methods that allow you to write almost any kind of test that you want. You can test that things are equal, that they're not equal, that they're two objects are the same. You can test if things are null, they're not null, test if things are empty, not empty. And in a minute we'll take a look more closely at will raise. But the assert class is pretty thorough, pretty complete, and you could certainly create a descendant class that would add to it if you wished. But it's a pretty complete set of test assertions that you can make in order to write your tests. Okay, so I talked about how one of the things you should test is you should always test how your class raises exceptions, and that it does in fact raise exceptions when it's expected to. So let's create a new console application here. I'm going to add a unit to it just like before. And in that unit, I'm going to create a simple class, just another class that we'll use for testing. Exception raiser is a class, and we're going to have a procedure called raise exception if for, and it'll take a simple integer as a parameter, and it will do one thing only. If a integer equals 4, then raise oh no, a integer was 4. And that's really bad. Can't do that. If we want to use exceptions, we need to, of course, add to our uses clause system.sysutils, like so. Save this out, and this should run just fine. Okay, it does compile and run, doesn't do anything. So I'm going to go ahead and create a new DUnitX project. Add it to the existing project group, create a test unit. I don't need setup, or I do need setup and tear down methods, like so. I'm going to use or add unit 8 to unit project 10. I'm going to use unit 8 and unit 9. And I'm going to declare a private variable, just like before. F exception raiser, T exception raiser, and we'll create an instance every time a test is run. And we will free it every time the test ends. And now we're going to go ahead and test that exception is raised, like so. And here is how in DUnit you test to see if an exception is raised. You assert that the code we're going to create will raise a specific given exception. So in this case, what we need to pass here is a simple procedure, an anonymous method that is a procedure that in fact calls our code. Raise exception if it's 4, and in fact we want to the exception class that we expect is exception. If we want to declare that class, we need it in our uses clause, like so. And we need an end at the end of our exception method. Let's make sure it compiles. Save the new unit. Make sure it compiles, which it does. And we'll run it. And we'll notice that we haven't written any tests yet, because I forgot to put the attribute on the method for our test, which we will now do. I'm going to save everything. I'm going to run it, and look, our test passed. And if we put it in the debugger, you'll notice that when the test runs, it does indeed raise that exception. Oh no, the integer was 4. But the test passes because this will raise method expects that an exception will be raised of type exception, and it traps it, captures it, and causes the test to pass. Now, of course, the opposite is true. We want to make sure that that thing isn't raised when it shouldn't be. So we'll create test that exception is not raised, and we will basically call this same code. I'll do the commit the cardinal sin of pasting in the interest of expediency, and I will now call will not raise. Get rid of this. Oops. Run it again, and you see now I have 2 tests passing. So that's how you handle exceptions in DUnitX. You simply pass in a anonymous method that calls code that you expect to have raise an exception. You tell them what kind of exception it expects to raise, and of course in this case it raises any kind of exception, but you could create your own exceptions, pass in specific exceptions, it doesn't matter. In this case it will not raise the exception. In this case it will raise the exception. The assert class will take care of handling and passing your tests based upon the execution of an anonymous method. Now, if you want to use DUnit, let's create a new test case for DUnit. Let's create a new test project. Call it that. Save it. We'll drag and unit 8 in to it. Unit 8, if I'm not mistaken, is our class, yes. And then we will then create a new test case using unit 8 and the raise exception if for method. And in this case, for DUnit, it's quite simple. You just simply set the expected exception variable to be an exception class that you expect will get executed in the call to raise exception if for. And again, we need to have sysutils in our unit. And now, if we run this, whoops. Now, if we save everything and run it, we should see that, again, this test passes. Oh, I didn't set a integer to be 4. I'm sorry. Now, once again, if we run it, we run the test, it does indeed raise the expected exception, and DUnit is pleased. All right, so let's take a look at a set of tests that are a bit more robust than what we've had before. This is a set of tests for my HTMLWriter open source project. This is a project that creates HTML based upon your code. And I have written for it a large number of unit tests, testing each and every method on HTMLWriter, ensuring that each one adds exactly the correct amount of HTML just as it's supposed to do. You can see these run if you like. They'll run, they'll pass. And what this enables me to do is to savagely refactor HTMLWriter. If I decide that the current algorithm or the current way that I'm building the string of HTML is not the way that I want it done, I can change it knowing that as long as my tests pass, HTMLWriter will still function as designed. And that's the real strength of unit testing, is that it ensures that your code works as it's designed to work and that it continues to work as it's designed to work as you make changes, bug fixes, and whatnot. A failing test would immediately show you that a change you made has broken something, and all the passing tests immediately show you that the change you made works as designed. And that's the whole goal, right? It's to keep your code doing what it's supposed to be doing. Okay, so far the tests that we've looked at have been pretty simple, and the classes that we've been testing have been simple as well without any real dependencies. And certainly I talked a lot about testing your code in isolation earlier during the slides. And so I want to show you now just a little bit about Delphi Mocks and how an isolation framework can be used to mock up or stub out, either one, dependencies in your code, enabling you to test your classes in isolation. So I have a set of demo applications that I'm going to use that will demonstrate the Delphi Mocks framework. The first one here is a simple stub demo called Simple Stub Demo, and it basically has in it two classes, a class and an interface. The iLogger interface we'll call log on a string, and you can log that anywhere. You can implement the interface however you like. In this case, it really doesn't matter. It could go to a database or a text file or something. Then we also have the class that we'll be testing and looking at, and that is the $to galleons converter. It takes an iLogger as a parameter on its constructor because it is dependent on an iLogger, and so good dependency injection techniques mean that you use constructor injection to pass into a class any dependencies that it has. It stores that dependency internally, and as you can see, it uses that logger whenever it does a conversion, as any good bank should do. It wants to log every conversion that it does. The real interesting part comes in the testing of this class. We're going to use the DUnitX framework to test our converter, and we're going to use the Delphi Mocks framework to both stub out and mock the iLogger interface. And as you can see, Mocks framework provides the ability to stub out the iLogger. You pass it in as a generic parameter, a parameterized type to tstub, which is in fact a record. And now I can create an instance of logger that is a stub of iLogger. In other words, it just implements the interface but doesn't do anything else at all. That allows us to then create an instance of $T to gallons converter, passing in the stub. We can then check the values of the result of the call to convert dollars to gallons, allowing us to check to make sure that the conversion is done properly. And we can run our assertion and then free our converter, and I'll be on our way. And here's a perfect example of a stub, right? We don't care about the logging. We don't want the logger to do anything, but we have to provide a logger. So we provide a stub logger that does nothing but allows us to create an instance of the class under test. Now that's an instance of using a stub to enable the class under test to be tested. But however, sometimes you want to make sure that the class itself is handling the dependency and doing something with the dependency while it's being tested. And you actually want the results of that dependency check, if you will, to determine whether the test passes or not. So what you use there is, as we discussed before, a mock. A mock, again, is a fake that can fail a test. So this time, instead of declaring it as a stub, we're going to declare temp logger as a mock for iLogger. And we're going to create it here. We're going to put in 2, and we're going to expect to get out 1. We're going to set the temp message to be converted dollars to gallons here using a formatter. And then we're going to do something curious here. We're going to take the temp logger, we're going to set it up, and we're going to expect that once when I call log, I'll use temp message. And you're going to expect that that happens somewhere down in the bowels of the dollar to gallons converter class. So temp converter, we create an instance of it. We call dollars to gallons. Oh, by the way, when we pass in temp logger when we create the instance of dollars to gallons. We then call the convert dollars to gallons method, and then we call verify on the logger. And this is really our assert. We've arranged, acted, and asserted. This is really our assert. Did the expectations get met? Did the thing that we expected actually happen? Did the log message get called with that message as expected? And the answer is yes, it did. Our tests passed. So that's a mock that determines whether or not a test passes based upon the behavior of the dependency inside the dollars to gallons converter. So that was a simple example illustrating the basic difference between a mock and a stub. Let's take a little deeper dive into the mock for our final demo. This is a demonstration of a credit card validator. There's an interface called iCreditCardValidator that determines whether the credit card is valid or not. Then we have an implementation of that interface here with the credit card validator. And then we have a credit card manager that takes that iCreditCardValidator as a dependency in its constructor, and the credit card manager can check to see if a card is valid, as well as process a credit card for a given amount. This is just a demo application here, of course. There's just a few things that we need to know. One is that a credit card will only be valid if it doesn't have a 7 in it. If there's a 7 in the credit card number, it's invalid. Again, just a simple way to invalidate a credit card for demo purposes. The real interesting part, again, comes with the tests. We're going to use the DUnitX test framework. We're going to have a test fixture here. We're going to ensure that the proper amount is returned when the card is good, and we're going to make sure that the charge returned is 0 when the credit card is bad. And this is just another example of using a mock. Here in the first test, we establish a good card value. There's no 7 in it, so the card is good. We're going to charge $49.95. We're going to expect to get $49.95 back when we do the charge, so we know that's what the charge was. And we're going to create a mock using the iCreditCardValidator interface. Now, once we have that mock, we're going to set it up such that it will return true when isCreditCardValid is called with the good card value. So when we call isCreditCardValid inside of the process credit card statement method that we have for the test, then we're going to ensure that that is the case, that it returns true. We're going to verify that fact, and then we're going to ensure that the expected result is equal to the actual result. And in the second test, we're going to do basically the same thing. We've got a bad card that has 7s in it. We're going to charge the same amount, but we're going to expect 0 because a bad card should return an amount charged of 0 and let you know that a bad card was returned. So again, we're going to return false when is credit card valid is called inside of the call to process credit card. So again, the mock is setting up an expectation that needs to be verified and validated when we make the call to the actual method that we're testing. So we can now run these tests, and you see that they both pass. And just for the sake of argument, if I change this to true, in other words, if I say that it will return true when a bad card is sent through, that test should fail, and it does. So that's another quick look at the use of a mock to provide information about tests and about the dependencies inside of other calls to other tests. And that should be about it. We've covered the gamut of unit testing, and we've seen how you can do unit tests, test-driven development, a little bit about mocking and isolation frameworks, and this is how you can reach me. You can get the code seen in our demos today under the Coding in Delphi portion of nickhodges.com at Bitbucket. You can find me on Facebook, Google+, LinkedIn, all the usual hideouts. And now it's time for questions.